In the last video, we introduced these second-order differential equations that we're going to be studying. And we said anytime I have a second-order differential equation of this form, so it's second-order, linear, homogeneous, constant coefficient, and as a consequence of all of that, it's also autonomous. Okay. It's going to correspond to a system that looks something like this. Okay. So I want to just compare the techniques that we have for solving these things. So over here, when we had these second-order differential equations, our technique was to guess. We were going to guess that y equals e to the st, where s is an unknown, e to a multiple of t, that this was going to be a solution to this differential equation. And what we wanted to do was then figure out what multiples of t would work. The reason this guess is reasonable, of course, is that if y is e to the st, y prime is just s e to the st, and y double prime is s squared e to the st. So all of my functions, y, y prime, and y double prime, are just multiples of e to the st. If I get the right multiples, it's possible that when I add them all up, they could cancel out and give me 0, and that, of course, is what I'm hoping to find. Okay. So what we did is we plugged in our guess. So we said, okay, as squared times e to the st plus bs e to the st plus c e to the st is going to have to equal 0. And since there's an e to the st in all of those terms, we factored it out. As squared plus bs plus c equals 0. And if two things multiply to give us 0, we know that one of them has to be 0. So either e to the st equals 0, except I know that it doesn't because e to any power is always positive, or as squared plus bs plus c is equal to 0. Okay. Now, if I look at this, that gives me a quadratic equation, and solutions to that are going to be values of s for which this e to the s times t will be a solution to my differential equation. Now, when we did this before, we actually wrote out the guess. Notice, I've just done it for a generic case. This shows that for a generic case, if I were to make such a guess and plug in, I would get an equation that looked like this. And notice, the a, the b, and the c that show up here are exactly the a, the b, and the c that show up here. So from this point on, because we've done it in the generic case, I know if I have a second-order differential equation like this, I can go straight to this quadratic equation, where I simply replace the second derivative with s squared, the first derivative with s, and the y with just the constant 1. If I can solve that and find the roots, e to those roots times t will be a solution to this second-order differential equation. Pretty cool. So that's a nice shortcut that we're allowed to take going forward. What I want to do, though, is I want to compare to how we would solve things over here. Because I don't know if I'm going to be able to get all solutions by this method. We didn't have a theorem about how I would get all of the solutions. But we did have a theorem over here for how I would know I had found all of the solutions. If I can find two independent solutions over here, an arbitrary linear combination of them will be the general solution, so that all solutions can be written that way. And the y that I'm looking for here is exactly the same as the y that I'm looking for here. So I want to be able to translate my knowledge about, hey, if I can get to this point, I know I found all solutions, so here's the general solution. I want to translate that to what we have over here. So over here, if I call this matrix A, I would simply say, okay, I want to find my eigenvalues and my eigenvectors, because if I can find eigenvalues and eigenvectors, I can build my solutions out of those. So I would take a look at this equation where I would say, let's take a look at the determinant of a minus lambda I equaling 0. So that would mean I wanted the determinant of 0 minus lambda, 1, negative q, negative p minus lambda. I would want that to equal 0. That's going to be negative lambda times negative p minus lambda minus a negative q, so plus q, has to equal 0. If I multiply that out, that's going to be lambda squared plus p lambda plus q is equal to 0. All right, now I've got this relationship between p and q, the coefficients that are showing up here, and a, b, and c, the coefficients that are going up here. So let's see if we can't compare these things. If p was just b over a, this is lambda squared plus b over a lambda, plus q, we had said was c over a, is equal to 0. Now if I multiply through by a, I'm going to get a times lambda squared plus b times lambda plus c is equal to 0. That's exactly the same quadratic equation I have here. It's just a difference in notation. When I'm talking eigenvalues, it's traditional to call them lambda. When I'm looking for which multiple of t do I want to take e to the power of, we usually call that s. But it's the same quadratic equation that I'm solving in either case. So that's very, very exciting. Over here, we called this equation the characteristic equation. So this would be the characteristic equation for our system. We can also refer to it as the characteristic equation for that matrix. Okay. Over here, would anybody like to guess what we call this equation? Yes, you're right. We call it the characteristic equation. So the characteristic equation that we'll use to find solutions to our second order differential equation is the same characteristic equation that we will use to try to find the eigenvalues that will lead to the solutions that we have for this linear system. So what we're going to do in the next few videos is just take a look at the different possibilities for the number and type of roots that we can have for the characteristic equation, and then say, what does the general solution look like here, so that we can figure out what the general solution looks like here.